Remember that we used Richardson extrapolation for the integration in previous chapters. It can also be used for the derivatives as well, because Richardson extrapolation is just addition of at least two integrations to be able to get a better approximation of the integration. Same idea for derivatives. Use two derivatives to get a better accuracy of the derivative. Two ways to improve derivative estimates when employing finite divide difference. Decrease the step size. So this is actually about the existing formulations that we showed in the previous slides. So in those, we usually decrease the step size to improve the estimates or accuracy, or use a higher order formula that employs more points. But these can be time consuming and can require additional effort. Instead, the third approach is Richardson extrapolation. Use two derivative estimates to compute a third one, more accurate approximation. And remember it from the integration formulation in chapter 22 or 21. And integration is basically just this formulation when we have two different step sizes and two different estimations of integration for those step sizes. And the result was like this. And for h2 equals h1 divided by 2, like this. When we can use the same for derivatives and just use this same idea. Instead of integrations, use derivatives like this. So we will have the same idea with two different step sizes. If we calculate derivatives, then we use this 4 divided by 3 and 1 divided by 3 subtraction to get a better approximation of the derivative. For centered differences, when you know that the centered difference approximations are the most accurate one compared to forward and backward finite divided difference formulations, the error is h squared. But for the Richardson extrapolation, for this one, for example, the error order is h to the power 4. So it's much more accurate, you can see. And the approach can be applied iteratively using a Romberg algorithm until the result falls below an acceptable error criterion. So you remember that we use Romberg integration in previous chapters. We can use the same idea, iteratively use this to be able to get a better result for the derivative. Here we have an example for Richardson extrapolation. For the same function as in example 23.1, where we use the forward, backward, and centered difference approximations, we want to estimate the same for x equals 0.5 and employing step size of 0.5 and 0.25. And the centered difference equation was this, if you remember, the simplest version, just with two terms. And with the Richardson extrapolation, we want to use this for two different step sizes, 0.25 and 0.5. So this is h2.4, maybe h2.25, and this is for h1, 0.5. So let's calculate this first for two different step sizes for h equals 0.5. So for this, we know that xi is 0.5 here. So we need xi plus 1 and xi minus 1 with 0.5 step size. So when we subtract 0.5, it's 0, and the result from the function is 1.2. If we add 0.5, the term is i minus I plus 1 is 1, and f1 is 0.2 from the function. So let's use these two in here to get the derivative with 0.5 step size. The result is minus 1, and the error with the true value here is 9.6%. Let's use the same for 0.25 step size. Of course, this time from xi, subtract 0.25 and add 0.25 to get xi minus 1 and xi plus 1, and use them in the function here to get the function values. Then use these function values in here to get the derivative. Over here you can see, and the error is 2.4%. Because we reduced the step size, we have a better approximation compared to this one. That's acceptable, but what if we use the Richardson extrapolation by adding these two? Here, if we add, we get much better result, which has actually a 0% error, it has the same exact value. The reason is that this is a fourth order function, and we said that this Richardson extrapolation has a fourth order error order, OH4, so it should give exact value for us. So this is how we can use Richardson extrapolation. In the Romberg integration algorithm, you can further add lower step sizes and use this with these lower step sizes as well to get better results. Up to this point, we used equally spaced data for the derivative estimations. If you remember, the step size, for example, was 0.5, and we were just subtracting it or adding it to the actual value to be able to get an evenly spaced data for x values. But what if we have data with unequally spaced values? So for the finite divided difference approximations, the data has to be evenly spaced. For the Richardson extrapolation, the data has to be evenly spaced and generated for successively halved intervals. So you know that we need to halve the interval in the specific case for Richardson extrapolation we used in this chapter or in this course. But empirical data, let's think that we don't have the function, but we have just data, then there can be like unequal intervals for the collected data, and in this case the finite divided and Richardson extrapolation are not suitable. So what we can do is we can use another derivative approximation method, which is called second order Lagrange interpolating polynomial, and it is useful for unequal cases. Let's see. So this is, if you remember from interpolation, this is the Lagrange interpolating polynomial with second order. So we need x0, x1, x2, 3 data points, and want to predict x, the function of x. When we take the derivative of this, the result is like this actually. Take the derivative of these with respect to x. Then I will not go into the details, but you can try this. And we can use this to have a derivative approximation with the data that we have with unequally spaced values. The advantages are it can be used to estimate the derivative anywhere within the range of the 3 points. And points themselves do not have to be equally spaced. And the derivative estimate is of the same accuracy as the center difference. So it's in a good accuracy. And for acute space points, it reduces to center difference anyway. This one. And the accuracy is in this order. So use this when you have unequally spaced data to get estimation of the first derivative. In this slide, we will see the derivatives and integrals for data with errors. And aside from unequal spacing, another problem related to differentiating empirical data is that it usually includes measurement errors. And the numerical differentiation tends to amplify errors in the data. So let's think that we have a data here with no error, for instance. But on the right hand side, we have a data with some errors. You can see there are some oscillations instead of having a smooth curve. So this modified slightly data means there are errors in the data. When we differentiate this, we will have a smooth linear curve because this, the tangents are linear here. The first derivative is like a smooth result because we don't have error here. On the right hand side, because we have errors, the derivative is also having some oscillations, and as said here, amplify errors. So the small errors will amplify these oscillations in the numerical derivative. So errors are amplified. The opposite side, when we try to integrate, in contrast, the reverse operation integration, moving from D to B, from here to here, by taking the area under D, so taking the area, tends to attenuate or smooth the data errors. So we have error here, but here we reduce the error when we take the integration, and it seems like a little bit more smoother than this one. So taking derivative amplifies the errors, taking integration dampens or reduces the errors, and these two are actually misleading, we can say. And we have to be careful on this when we have data with error actually. Maybe you can try better integration or differentiation formulations to get more accuracy, but still this issue is always there. Just keep this in mind. There are some numerical methods for partial derivatives as well. Up to this point we learned about the regular derivatives when we have only one input value, or like x, then it's just a derivative with respect to x. But what if we have more than one inputs, x and y for instance, for the function? Then we will take a derivative with respect to x as well as a derivative with respect to y, as you can see here. In this one we can use the centered difference approximation again. For instance, for delta f divided by delta x, we will have this centered divide difference, but we will just have a difference of step size of delta x. So the step size will change in the x dimension. So this is two-dimensional, you can think of, and the step size is delta x. And x plus delta x is like x plus h and x minus h, if you remember from the centered divide difference formulations, and y will be constant. In the derivative with respect to y, then we will add the step size to the y dimension. X will be constant, so y plus delta y and y minus delta y, and here the h is delta y. For mixed partial derivatives, first form a difference in x of partial derivatives in y. So first try this, for instance. Once you take the derivative, then try this. So this mix means we have the derivative both with respect to x and y, as you can see here. We can need this too. So first take the derivative for this one, for instance, then for x. Simply it becomes like this. After having the derivative with respect to delta y, for instance, here it took the derivative with respect to delta y over here, but we have the finite difference of x of partial derivatives in y, so x plus delta x, but this shows delta f delta y because it remains that way because we are using delta x here as the finite divide difference. Here x minus delta x and delta x. Now after this we will use the difference for y as well. Let's move on. In the second one, evaluate each of the partials in y. So we will have y plus delta y as well. Y plus delta y. For this one, we have for this y value y plus delta y minus delta y, and x plus delta x remains here for these functions, and divide by 2 delta y for this term. For the second term again, x minus delta x remains, and two function values of y plus delta y and y minus delta y divided by 2 delta y, and this is divided by 2 delta x from here. So this is the formulation. At the bottom you can see here, this is the formulation for delta square f delta x del y, mixed partial derivatives. And because we didn't use y plus delta y and delta minus delta y here, we are using now that here, y plus delta y, y minus delta y for this term. And for this term, so of course x plus delta x remains the same. Here x minus delta x remains the same, and y plus delta y and y minus delta y. Two additional terms, and this is the general formulation, as you can see. When we organize this, we will have the final version with these values at the denominator, and these are the four terms you can see here, with x plus delta x constant, differentiation with y plus delta y, difference actually, y plus delta y and y minus delta y function values. Same here, this time x plus x minus delta x.